So, hello everyone and welcome to our webinar in cooperation with ST Microelectronics. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is migration to USB-C, how to meet EMC standard, effective protection and high interoperability. Our speakers today are Andreas Nadler, who is working as Field Application Engineer at Würth Elektronik eiSos, and Benoit Fauré, who is working as Product Marketing Manager at ST Microelectronics. They will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 50 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will receive the link to the presentation as well as to the recording of today's webinar only in the next few weeks. And now I will hand over to our speaker, Benoit, and I wish you an exciting webinar.
Good afternoon. My name is Benoit, and I am in charge of USB PD controllers at ST Microelectronics. I am based in Grenoble in France. Here is the agenda for today. I'm going to quickly explain the paradigm change and motivation from people and companies to migrate to USB-C, universal charging. I will then highlight migration risk and protection concerns. Finally, I will share design guidelines for a clean implementation on sync side in order to guarantee both safety and interoperability. Market trend. The market is evolving today. There are plenty of portable battery-powered devices with different power capacities that need to be charged quickly, anywhere, and at any time. So carrying many kinds of AC adapters is a mess. There is always one missing, and the young connected generations are looking for simplicity, portability, but they are also sensitive to their environmental footprint. This is why 100 watt universal charging based on USB-C can cope both with charging technical requirements and young people expectation and way of life. To achieve this, the industry is innovating and is working on replacing external AC adapters with custom connectors by simple USB-C cable. So on sync side, which is our focus today, custom power plug as far as they are below 20 volt and 5 amps, and USB micro B plugs can be replaced by a unique USB-C connector. This means that all the micro B devices will sooner or later migrate to USB-C, but also that non-USB products are now eligible to universal charging. That's why USB-C is a game changer. On source side, all new chargers in the computer and smartphone industry are now developed using a USB-C connector. And the challenge today is to increase the power density or to integrate the AC-DC power conversion into walls using GaN technologies, for instance. Different reasons are pushing organizations to adopt USB-C, as illustrated by this communication from USB Implementer Forum: reusability, sharing, electronic waste reduction, and improve user experience, but also local legislation or governments worldwide that are pushing this way. On technical sides, there are also many motivations for designers. For existing micro-B devices, getting more current or more power allows to charge faster or to increase the battery capacity and to gain in efficiency. For custom power plugs application, adopting a standard connector improves the product design and the user experience. For AC-powered device with captive cable, there is also an opportunity to move from EV AC-DC conversion to a more effective DC-DC power management unit. This chart is to let you know that ST is sitting at the board of directors together with other leading actors from the industry. So many people are contributing to the spec review. Some of those are stated here, and some of them are involved into 2 hours weekly calls every week. So the standard is, and what is behind the standard is well known for us and allowing to fine tune our products for every application. This is a picture of our USB-C and PD Interface IC portfolio, which is designed to address most use cases with the appropriate partitioning. There are many different ones, and today we are going to focus on 5 volt only and 520 volt charging application on sync side using 2 controllers. The first topic to start with is not the USB PD protocol and the standard. That could be boring. We are going to speak about what you should know at application level before starting your migration to USB-C. So USB-C is no longer a data-only protocol. Thanks to smartphone, legacy USB has become more a charging protocol than a data one. And today, USB-C can deliver up to 100 watt, 20 volt, 5 amp. And when there is grid power, there is also a grid responsibility for the designers. So migration to USB-C has to be considered from a power management perspective first. So here is an illustration of bad buzz on the web a few years ago because of some wrong implementation of early adopters combined with a cheap or non-certified USB-C cable. So when playing with power without appropriate care, this can be destructive. Same lesson learned for the famous Raspberry Corporation, believing that migration at 5 volt would make no difference. They originally tried to make it cheap with a simple mechanical connector swap with discrete, but at the end they had to redesign it properly, having made some bad buzz in between. So there are many other examples you can find on the web from Nintendo, Samsung, or others having met troubles in past implementations. So why is it a bit more complex than it looked like? Because of several reasons. First, because 5 volt and 20 volt devices can be plugged together mechanically. AC adapters can also be plugged together. The power, as defined by the standard, can be bidirectional, so it can flow in both directions depending on what controller says. We need to protect from non-compliant or low-cost devices available from the open market, and we need to protect from cable issues. One word about protection, what the standard says. It doesn't tell too much about protection, but it highlights that you have to take care to a minimum that are listed here, depending on your application world, depending whether you are a source or whether you are a sink. Note that a device should not rely or trust the attached devices to ensure its own protection. So that's why ST controllers implement many protection mechanisms which are natively integrated and merge with the protocol itself and other operational features. Back to our subject, let's discuss about how to properly implement USB-C as a replacement of DC barrels or custom power plugs or micro-B ports. What designers must know before starting their first design is that while legacy USB was hot socket, 5-volt power was always available on VBus whenever a device is connected or not. The USB-C implementation is cold socket on both sides. So the source powers VBus only and only if a sink is attached and identified properly. A sink let VBus flows on VIN only and only in if a source is identified properly and if VBus voltage is meeting the power negotiation results. So to do so, dedicated active controllers are mandatory on both sides. So we need to consider protecting by default every USB-C port to 5-volt shorts or more, even for 5-volt only applications, as not only 5-volt can be available on the plug. As shown on the picture, different kind of 5-volt or more connectors can be replaced by a single watt. Implementation will rely on different USB interfaces IC or ICs with different settings. So our ST-USB4500L controller can be used to migrate 5-volt connectors to USB-C, while ST-USB4500 PD sync controller must be used and configured to support any 6-volt to 20-volt application. These mini dongles allow quickly external prototyping with a limited footprint before it is integrated in the final application. The main controller is called ST-USB45 and is dedicated to any USB PD application up to 20 volt. So it can be customized to support any application with only basic know-how about the standards and limited software skills. So no need to be an expert at all, thanks to the graphical user interface. Thanks also to open source Altium libraries, schematic and optional software libraries. A spin-off version called ST-USB4500L has been done for pure USB micro:bit migration. It is even more straightforward to implement as the 5-volt optimization is already done by ST with a specific commercial product. So we can say it's plug and play. Let's start with a 5-volt only use case. So this slide shows a traditional implementation relying on legacy protection switch, a 5-volt or discrete USB-C controller operated by an application processor. Among all functions that must be implemented to make it work properly, some, in red, are poorly or simply not implemented in most cases, resulting in interoperability or protection issues. For instance, the discharge and the restart management are frequent issues. Using ST-USB45L, which is designed in mixed signal high voltage technology, the IC is protected up to 28 volt. Therefore, it can be powered directly on VBus on source side, even if the battery is at 0% and if the MCU is unpowered. It is able to support dead battery mode, identify a source, check incoming VBus power, then drive the protection switch, and report finally the available current to the MCU or directly to the battery charger. It is available in QFN and CSP package, and it is certified. So such a solution is standalone, plug and play, and require no software skill or PD know-how to make it work. In short, here are the features that are supported. Dead battery mode support. No battery or MCU is required, which guarantees safe and ultra-fast power up. It is powered directly from VBus, so zero leakage at all on the application battery, which is extending the battery lifetime. It performs under and over voltage protection, of course, and it implements automatic power budget reporting, which is the duty of the sink, in order to set the maximum charging current and prevent from collapsing the source. And it implements especially error recovery mechanism in order to restart from a false condition. So the key point here is that compared to traditional schematics, the protection switch is opened by default at the attach and closed by the controller itself only when electrical conditions are correct. While in the standard implementation, protection switches are usually closed by default and open only when a fault occurs. And this might close again separately from USB-C negotiation, leading to interoperability issues. Sorry. So here is a commented schematic. As you can see, implementation requires very few components. So it's pretty tiny, safe, robust. It's fast to implement and it's certified. So you can see here the plug, the IC, some discharge paths, the protection switch, an optional I2C interface, and signal to drive directly the battery charger. So what ST-USB45L brings to your design, the main value are safety and interoperability, which are a must today as USB-C is being largely adopted on the market. So the cherry on the cake is that the zero power consumption, we can say, which is key for battery powered device. So it operates without being connected to your battery. It takes power directly from the source. Then, because the product is standalone, implementation is straightforward, which makes this product good for mass market. And also, please note the availability of CSP package on top of QFN package. To support quick implementation, all PCB databases are available freely to enable half-a-day integration into a larger design. Optional software is also available for application with advanced user interface, but software is not necessary at all. Similar approach can be done for 5 to 20 volt application. So this permits to migrate to USB-C new applications such as professional drones, smart speakers, even power tools, or any kind of toys or robots, personal electronics, personal care device, and so on. Above 5 volt, implementation is very similar to the 5 volt use cases, and it relies mainly on a controller IC and a protection switch. As some more complex use case can be managed with ST-USB4500, it integrates two customization methods, a non-volatile memory and also a RAM memory. So this allows to customize the IC during either manufacturing, mainly for application without MCU, or even to change the charging profiles on the fly directly thanks to an application processor. Everything is possible and flexible. Up to 2 custom power profiles can be configured and enabling to support custom charger and a universal charger as well, on top of the 5 volt, which is mandatory by the standard. A full feature evaluation board is available for convenient hardware and optional software prototyping. So with this board, you can access the main power path, but also discriminate the power path, the power profile. A small footprint dongle is also available. All USB-C connectors and passive components, of course, are coming from Würth. This is a key point because the certification works for the IC, but also for the connectors. So the full chain has to be certified. All tools and collaterals can be downloaded online. So we have one reference design, 2 boards, 1 graphical user interface, 2 software libraries, and some additional documentation. So because the device is also convenient and easy to use, there is a large community of developers that also offer additional boards and software developments for those who want to look at on GitHub community, for instance, but also Tinde, Arduino, SparkFun, and some others. So as a conclusion, the key takeaway from this presentation are to focus on the safety first and then on interoperability, which are guaranteed using ST and Würth components. We have a very small reference design and open source collaterals online you can access for a very fast implementation. Thanks for your attention. I will let my colleague Andreas continue with his presentation.
Good afternoon, everybody. Welcome to the second session of the USB Type-C seminar. I call it Superspeed Seminar because we are talking now more about terms of EMC, terms of layout, terms of components for protection. We made a measurement for you with a 5 gigabit per second dongle, and I give you a short overview in the beginning about USB history and a short mechanical overview about the USB-C connector. Let's start. So it all started in 1996. From a, let's say, from today's point of view, very chilly 1.5 Mbit per second. Nowadays, from August 2019, the USB 4 is released. So this means we have now speed up to 40 gigabit per second, and it's all based in principle on the Thunderbolt 3 protocol from Intel. So this means for you, it can be one interface to do it all, because not only a key, a mouse and a keyboard and some food warming devices you can connect. Also, you can connect 8K monitors, you can do some HDMI, you can do other protocols and so on. You can connect Superspeed SSD, external devices and so on. And again, 100 watt of power, as you already heard. So with USB 2.0, we had 4 different connectors, mini, micro, A and B, you all know. We had a maximum data rate of 480 megabits per second and a maximum power of 0.5 amps and 5 volts. In 2008, we had USB 3.0. Then we get one more micro plug and we skipped the mini plug. And there we had maximum data rate of 5 gigabits per second and 900 milliamp at 5 volts. Then after 3.0, we got in 2013 3.2. And then we introduced the USB-C, or the USB Consortium introduced the USB-C connector, which has the main advantage, and you can flip it 180 degrees around, so there is no need to look if it's in the right direction or not. And we increased the power from 5 volts to 5 amps. Then we have 25 watts of power in total and 10 gigabits per second. And now, as I said, we are only at USB-C. All other connectors are not valid anymore for USB 4 and USB power delivery. Then we can go up to 20 volts and 5 amps, which results in 100 watt of power we can deliver. A short look on the connector itself. We have 24 pins, which means we have in the middle the legacy USB 2.0 interface. Then we got the configuration channel where we can communicate, as you already heard, which kind of device, how much power and so on. Then we have the sideband channels. We can use them if you have no USB protocol, for example, MHL or HDMI. Then we use these channels. And then we have the V-bus channels, which we need for powering. And then we have the Superspeed channels here and here, where we can go up for 2 lanes for 40 gigabits per second and maximum. And we have the ground pins for the return path of the current. From a mechanical point of view, you should stay below 30 milliohm of contact resistance. And you should have at least between 1 and the second pin 100 volts dielectric resistance. As we heard, the maximum voltage is 20 and 100 is 5 times higher, but of course we go even higher than this. Our connectors can handle up to 1000 volts, and if you see here, if you go with 1.5 kV, which means we have a carbon path between 2 pins in the LCP, which is not flammable, of course, but then the connector you cannot use anymore, but 1.5 kV is more than enough. with ESD contact, you go to the shielding and not to the pins, so there is no need of higher voltage rating there. If you look how what are the terminal let's say requirement of all, then we see the PCB, we see the cable, we see the connector at 3 amps, and we can see the connector is the weakest point from a terminal point of view. We have around 12 Kelvin of self-heating, which is not critical, and the cable has approximately 9 Kelvin, and our PCB we used for the dongle or for the adapter here is only 5 Kelvin. This depends on your PCB in the end, but it's the let's say the strongest point. And even 12 Kelvin at self-heating with 3 amps of current is not critical. Absolutely, we made the measurement in 22 degrees of room temperature, of course, in a normal lab. If you go to the limit is actually 5 amps. So we have, in our case, 10 Kelvin of the PCB, and the maximum is the connector, again, with 23 Kelvin approximately. Self-heating, which results in a total temperature of around 45 to 50 degrees, which is absolutely not critical at all. And even if 8 amps, you stay within safe lines, but 8 amps is out of the spec, of course. The insertion on extraction force, we have between 5 and 20 Newton. Usually we have at least 10 to 20 Newton, which means you can hang up 1 kilogram of weight at least, because this 10 Newton is around 1 kilogram, of course. Then we say, the USB Consortium say you need to handle at least 10,000 cycles in extraction on insertion, and then you must stay below a certain value of RTC of the pins. This is especially critical for the V bus and the ground pins, of course, because there we have the highest power and the highest current. But with our industry grade connectors and receptacles, of course, we can handle 30,000 mating cycles, which is more than enough for most applications. And then we got a slightly increase in the RDC, which results then, of course, in a greater heating of the connector with the full current. But 30,000 is absolutely no problem for the connector. If you look at the shielding, the USB Consortium say you need at least 4 connection points for the shielding. We provide at least 6, and sometimes even more. The more connections, the better for the shielding effectiveness, of course. And so with our material, we use stainless steel in high quality. We have a very robust connector, and the stainless steel provides excellent H field and E field shielding of the connector and the cable. Of course, you need to use a high quality cable, especially with higher data rates, and not any cheap cable from the Far East. Most of our industry customers are still using USB 2.0. The reason is they do not need more speed, but of course everything is going faster and faster, even in industry. And I have the experience with most of the customers. I see designs like this, which we have some, let's say, mistakes in the design, where usually you know USB has a differential impedance of 90 ohm, and if with this routing here, and this layer change here, you for sure will not keep the 90 ohm impedance in your system. Luckily, USB 2.0 is, let's say, even with 480 Mbit, slow enough to guarantee you the function of the data signal and so on. It's still working at most of the customers, even with bad design. But from USB 3.0 and more, designs like this are not valid anymore. You have also seen this example, the customers which have done some layer change and had very long microstrips, and the data loss was exceptionally high. So it's not really working anymore. So you need passive components and routing which is suitable for the high-speed design. For example, I give you a small, let's say, rule of thumb. USB 2.0 with maximum speed and the system impedance. Maximum speed means we have a fundamental frequency, which is half of the 480 Mbit. This is 240 megahertz, the maximum fundamental frequency of the data signal. This means we have a wavelength of 120 centimeter. And what I said, a rule of thumb, it's not 100% correct, but a good rule of thumb in point of EMC and in point of EMI and in point of data signal loss and package loss. Impedance transformation below 1/10 of the wavelength is negligible, which means in this case, every structure length on the PCB, on the cable and connectors below 12 centimeters is usually not very critical to the data signal. And therefore you can violate the 90 ohm very heavily there. And you will, even then you will have a good, or let's say not a good, but you will have a signal which is still working. Everything over 12 centimeter length could be then a problem. Could be. Must not be. It could be, depending on the environment in your application. But if you take an example, and for our next measurements we did USB 3.0 with Superspeed with 2.5 gigahertz, then we have a critical length of 12 millimeters. And 12 millimeter is pretty short if we sum up all the components on the PCB, the plug, the cable, and so on. So failure in the design will be punished very fast and very hard then, and you will have a lot of data loss in the end. So a much more careful view on the design is necessary. And for example, if you have a PCB which you would like to route the high-speed or super-speed layers on top and on bottom, then it's not important if it's USB, it could also be MHL, could be HDMI or 10 gigabit Ethernet and so on. Every high-speed pair or a single-ended high-speed signal, if you have it on both sides on the PCB, you need at least a 6-layer PCB, because only then it's guaranteed that every data signal has a defined ground return path on the same distance to guarantee the system impedance. So then the distance here can be the same and the distance here can be the same. And if you only have a 4-layer PCB, which you have then VCC and ground plane in the middle, then the distance from this side to ground is maybe correct, but the distance from this side to the ground is then different because the VCC is in between and the capacitive coupling is even higher then. And again, to get a very good power integrity in the system, it's recommended that your power ground sandwich here should be, the distance between the two planes should be lower than 100 micrometer. Then you get a good plate capacitor, which has a very low impedance over a wide frequency range and can provide a very good current, let's say HF current or RF current to the system. And in the end, this is the best compromise for decoupling, power integrity, EMI, signal integrity, and self-disturbance of the system. And if you cannot avoid, let's say you need to go from top to bottom layer with a wire, then it's very important to give every high-speed signal at least one ground wire in the correct distance to hold the system impedance in the vertical line as well as in the horizontal line. And the rest rings in the middle of the PCB should be avoided to minimize capacitive coupling to other layers, not only VCC, but also to any, let's say, signal layers in between. This is mandatory then to get really a clean high-speed design in the end. There are tools which help you to calculate the correct distance. Also some formulas in the internet if you would like to use. So that's not a miracle, but you need to leave, not two are better, one is in the, usually enough. So what we did, we create a dongle, which is intended for 5 to 10 gigabit per second. We show here that it's not critical to put in combo chokes for better EMC and EMI performance, and ESD protection on this side to provide better ESD immunity. And we also provide here a 5-pole filter for filtering the power of 100 watts to get out the differential noise there, and also some ESD protection. And if you do a proper design, the rest of all, even with these components inside, it's not a problem to get a 5 to 10 gigabit and more over the site, for your data signal. How did we test this? We had a 4-port network analyzer, which has a differential impedance of 100 ohm. So 90 ohm is not possible there. It's only 50 ohm single-ended or 100 ohm differential. Therefore, we made a 100 ohm differential adapter. In between cable and adapter, we plugged in the dongle here, and the microstrip here is also then 100 ohm to get the same all the time, and then we measure it back. We make a time domain reflection measurement, where we can see the influence of every component due to the impedance of the PCB, and we made an eye diagram to see if the signal is still not interrupted or disturbed. So what we need there, we have for the USB2 Legacy, we have ESD protection, we have COM mode chokes for better EMI and EMC, and as well for the Superspeed lanes, COM mode chokes and ESD protection, and we have for the control and for the power path, we have also ESD and filtering. So there we see it on the top from the CAD program. We have here the low speed line, we have here the control signals and the sidebands, and we have here the super speed lines, which are the most critical in this. And here we have the 100 watt power path, 20 volts, 5 amps. Of course, for the super speed lines, we need special HF or to say RF combo chokes, which has a very low strain inductance. For the low speed, we do not need a really very special combo choke, but a proper one, of course. The same for the ESD protection. We need here very low capacitance parts, which have only 0.05 picofarad of channel-to-channel capacity. And here we have a bigger one, which provides you easier implementation because you only have to place one part. Important is for these parts here, you can easily put it on the microstrips because you can route through the parts directly without any angles. And this is very beneficial in RF terms of view. And for the power path, we have one high pulse ferrite and the second high pulse current and inductor for the lower frequency range. These both working above 10 megahertz. The inductor is working below 10 megahertz, and we have two ceramic capacitors for filtering. We see the graph in the next slide. And we have one TVS diode, a small one, which can handle 20 volts. And all these ESD protection devices can handle plus minus 30 kV, so more than enough for every EMC test and also for the, let's say, normal life in use then. So what is important, if you look at the combo chokes, then we have in all the data sheets of the RF combo chokes, we have the insertion loss over the frequency. Then we see here the maximum of 10 gigahertz, which results then in 20 gigabits per second, for example. We see this combo choke has up to 10 gigahertz, only 3 dB of insertion loss, which is quite low. Then if you look at the insertion loss of the TVS diode for the super speed lanes, you only have 1.5 dB of insertion loss at 10 gigahertz, which is also pretty low. And for the lower speed lines, we use this bigger one, which has approximately minus 3 dB at 7 gigahertz. So also not bad, but not suitable for very high frequency devices. So what happens if you put in a standard speed, let's say, combo choke, which is intended for example, USB 2.0 in a 7 gigabit signal, then you will violate the eye diagram due to the higher strain inductance, which means the rising edge and the falling edge of the signal is too slow then because of the too much inductance in the line, and then the signal is fail off, let's say. If you use really a HF component, which is suitable for the high-speed designs, then you will have enough speed or enough, let's say, slope in the rising and the falling edge, and your signal is not disturbed and working properly and fine. Important here in the diagram, if you do not look in the insertion loss, but on the strain inductance, you see here the difference. This is the strain inductance of the low-speed choke. This is strain inductance of the high-speed choke. There's a much more bigger difference because we're in a logarithmic scale. And of course, the advantage of the low-speed choke is it has a higher common mode inductance, but it doesn't help you if you disturb your signal. If you look at the power path here, so we use, as I said, a 5-pole filter here with one ferrite here, which is very pulse robust, which do not die due of current pulses. It's the MPSP series. Then we have here the MAPI series, which is a small device with a low RDC, which helps to attenuate below 10 megahertz especially, and two ceramic capacitors with 4.7 microfarads. And in the end, we get a result from a very good result from 1 gigahertz to 100 kilohertz. We have a broadband filtering there and get out all the higher harmonics of the power supply. And the temperature is around 65 degree maximum power of the choke then, and your voltage drop is around 115 millivolts, which is also not critical. You see here the terminal, of course, the inductor is the hottest point. It's the part of the highest RDC. Therefore, if you spend, let's say, a little bit more bigger component size, then you get lower RDC and then the temperature is also lower. But 65 degrees at maximum is not critical in room temperature. Okay, now we made the test. In the end, we should stay below, let's say, outside the red area to get the free eye diagram. And let's have a look. What you see here is the time domain reflection measurement, TDR measurement. It shows you the system impedance over different parts of the PCB of the, let's say, of the whole test setup. There we see the impedance of the test fixture, which is around 100 ohm as expected. Then we see here the influence to the impedance of the plug, which is 90 ohm is here, so which is a little bit lower than 90 ohm, but it's normal for all manufacturers of plugs. You cannot avoid this a little bit. So it's lower than it should be, let's say. The PCB itself is 100 ohm again, as it should be due to the rest of the fixture. The other receptacle is a little bit better than the plug on the left side. It's a little bit closer to 90 ohm, but both of them are not critical. And the cable is also a little bit around, let's say, at this first part of the cable, a little bit below 90 ohm, and then it's very close to 90 ohm, the cable. So it's a very good cable then. And the eye diagram without any other components here, only the microstrips and the plug is perfect good, as expected. Now we insert the combo chokes here. We have the same, the test fixture, no difference. The cable, we have a little bit shift in the resonance due to the stray inductance of this, but it's not important. The plug stays the same. With the combo choke, we came even a little bit closer to the 90 ohm here, which is okay. And the rest is also nearly the same due to the stray inductance of the chokes. It's a little bit different, but not much. And important, the eye diagram stays clean. So the next 5 gigabit per second test we made with additionally the ESD protection diodes. There we see the test fixture again, the plug again, the combo choke influence. The curve looks a little bit different now due to the, let's say, very, very small capacitance of the components. We have 0.05 picofarad, and this is a little bit another, let's say, resonance point with the stray inductance, but it's all within the limit lines and within the, let's say, critical line, so no problem at all. We stay in the range from 90 to 95 ohm. And important, the eye diagram stays clean. So in the last you see here, there is no coding on the microstrips. As you see often in RF designs, there is no coding because every coding has some kind of epsilon R, which increases the dissipation factor and decreases the signal quality then, of course, because every rectangular signal has infinite sinus waves inside, and the higher frequency sinus content will be reduced then with a higher epsilon R. So what we see here then, we see a little bit, as you see here in this area, if you put in here now the coding, we have an influence in the impedance. This was expected, but in the end, it's impossible. The eye diagram stays still clean. And this is due to the fact that we have a very, let's say, straight design. We have not too long microstrips here. We have no sharp angles. We have no layer change and anything else. And we chose the right components for the signal quality. And even if we speed up to 10 gigabit per second, now we made all the tests with 5 gigabit, with 10 gigabit per second. And if we activate the USB equalizer, which usually have every chip have a USB equalizer, to adapt the signal to the cable length, because we can have different cable lengths, then we need different equalizer settings. But even then, the eye diagram is 10 gigabit per second and all protection components stay clean. And comes to the end, if you would like to test some source or sync with 100 watt and with the SD controllers, we have some development kit together with SD, which is working pretty fine, where you can make some pre-appliances. You can make some tests before the development with your, let's say, desired functions there. And that's all from my side. Thank you very much for listening. And now we're looking forward to your questions.
Okay, so thank you, Andreas and Benoit, for your interesting presentations. As you have mentioned, now we would like to turn our attention to your questions, and we wait a little until some questions come in. So let's start with the first question I see. I think I can answer it already. Can I have the presentation to share it with my team? Yeah, we will send you the link to the presentation as well as to the recording of today's webinar only in the next few days. So then let's go on with this next question. What are benefits of using a code I2C with the controller?
Okay, so yeah, it's a good question. So it's true that the software support is not required at all to perform the negotiation and to ensure the safety of the system. But for some complex application or application with an advanced user interface, such as the screen, etc., it's always convenient to report the USB-C connection status or the negotiated operating power. So some customers use it to collect the source power profile or also optimize the charging strategy, for instance.
Okay, thank you, Benoit. Then let's go on with the next question I see here. What equipment are you using for impedance analysis on the filter board? It looks like sort of reflectometer analysis.
Yeah, I can answer the question. You can use different equipment, of course, but we use usually from HLand an impedance analyzer there. We have the possibility to get current and voltage to the filter on at the same time, and then we see also the DC biasing of the capacitors and the DC bias of the ferrite, because capacitors has a derating with the voltage, and ferrite has a derating with the current a little bit. There we can see this, of course.
Okay, thank you for the explanation, Andreas. So let's go on with the next question. Is it preferable to route all USB-free differential signals with curved tracks instead of angles?
Definitely yes. If you have angles, of course, if you think about a 90-degree angle, then on the corner of the angle, you have a different width of the microstrip than the rest of the microstrip. And the bigger the angle, the best is to curve then, of course. Then the most stable the width of the microstrip. Therefore, we have no E-field concentration there. And the second advantage is we have a stable 90 ohm, the most stable 90 ohm impedance if you route correctly the rest then.
Okay, thank you. Then let's go on. With USB-C, what do you do with the shield connection? Does it get decoupled to 0 volt?
This is depending on your application. In the end, usually a shield of USB is often a PE connection, so protected earth. But it must not be, because for example, if you have a smartphone which has a plastic shield, a plastic housing, so there is no protection earth. In this case, so let's say first, the best is you connect it to protection earth if there is no electrical issue in your application with this, because then you have the best path back to the earth and let's say the lowest impedance path back to the earth in terms of ESD and so on, because every ESD impulse is referred to protection earth, and then you will get it back to protection earth as fast as possible and not in your PCB. And if you have a plastic housing, then you can, and maybe you should connect it to a local digital ground. And your digital ground should be then, let's say, a bigger plane inside your PCB, and then you get automatically capacitive discharging to the ground back, because every device in the room has some pico or femto or nanofarad, depending on the size, and therefore the ESD impulse, for example, is routed back to the earth through the, let's say, parasitic capacitor of your device.
Okay, thank you. Then let's go on. Next question. Can the ST USB4500L and ST USB4500, can they be used in USB data application?
So the answer is yes, of course. A USB data controller can be implemented in parallel of the USB PD controller. And it can be scaled to either USB2, USB 3, or soon USB 4. So the reason why controllers are not merged together is because the PD controller or USB-C controller is designed in mixed-signal technology to support the high voltage, while the data controllers are usually embedded in the application processor, and it's better this way.
Okay, thank you, Benoit. Then as we have a look at the next question, just a hint from my side, if we can't answer your question now, we will answer it later via email. So then let's go on. Is the ST USB4500 able to protect from non-compliant power supplies?
So yes, the PD controller has to make several checks before it powers the system. So it will power the application power pass only when a source is properly identified, when it starts initially at 5 volt as expected, and then it has to perform a power negotiation and respect some timings, which are defined by the protocol. So if the electrical voltage are not in line with the negotiation and not in line with the protocol, then the controller will immediately open the switch and disconnect everything, and then renegotiate from scratch a new negotiation process.
Okay, thank you, Benoit, for your answer. So then let's go on with a longer question I see here. When ESD testing, our test lab always insists on testing contact discharge by placing the ESD gun inside the opening of the USB connector. Is this a valid approach to testing USB-C connectors? And second question here, would the application examples shown be immune these test conditions?
So as far as I know, usually you have some kind of a test finger, and if the test finger can touch the pins, then it's mandatory to test these pins. But if the test finger is not able to touch the pins directly, but only the shield, then my point of view is you only need to make an ESD impulse on the shield and not on the pins. But if, because of any reason they insist on it, of course, the components we had here, they are suitable for 30 kV plus minus. So the normal ESD test should be no problem for the components there, and for the dongle there, you can order this dongle as a complete mounted PCB for testing in your device, for example. Then you know it for sure. But in the end, yes, it should work with these components on it.
Okay.
But it should not be necessary in this testing.
Okay, so then I think we have time for a few more questions. Then let's go on with the next question. How complex is the ST USB customization?
Okay, so two cases for the 5-volt only device, the 45L. It's straightforward. It's no need any customization because it's fitted to a limited number of use cases at 5 volt. And for the high voltage one, the 4500, so it can be configured either through a non-volatile memory or by software. So for the non-volatile memory, you have a graphical user interface, or you have some dedicated software to run during the manufacturing phases, and it takes about 40 bytes of I2C words. And it can be also done at any time from an application MCU in order to align USB PD port profile and application requirement, for instance.
Okay, thank you for your explanation. So then let's go on with the next question. What is the voltage of USB-C if used without control?
So by default, USB-C protocol is a cold socket, meaning that a source should not apply any voltage at all on the bus until the source is able to identify properly a sink, meaning that if you connect only a cable, there will be no power. If you connect a device that is not identified as a sink, there will be no power. But potentially, when you are a sink, you can be applied at the connection any voltage in between 5 to 20 volt in theory, and in case of some discharge issue, for instance. So you have to consider that voltage is scalable and might be anywhere in between 0 volt to 20 volt at any time.
Okay, thank you. So then let's go on with the last question here. Can there be problems with disconnects of data transmission during or after the EMC disturbances? And can there be countermeasures or retry mechanisms?
So, of course, there are different criteria in the EMC test, depending on where your device is intended for. For example, if you have a medical device, it's not allowed to get any data loss, for example, from the patient heart rate and so on, even if the signal retries by themselves. So for a standard, not critical industry device, it's often allowed to, let's say, lose shortly your screen or lose shortly some kind of measurement data if the system can retry it by themselves again during the EMC test. It's very common, of course, during burst or during ESD or during any other immunity testing that you lose some connection, not even USB, but also CAN and Ethernet and so on. And depending on your device area where it's installed, it's allowed or not to lose this data.
Okay.
But from our components, let's say we cannot help there to retry this again. Let's say this is in the end some terms of software to get retried in very fast time then.
Okay, so now we are finished with our webinar. If there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Benoit and Andreas, for this great webinar. It was a pleasure for me.
Thank you. Have a good day.
Thank you. Bye.
Yeah, also from my side, I hope you will hear us at our next webinar, and I wish you a good day. Goodbye.